Okay, in this video, I'm going to give you an explanation of the little magic formula that I gave you towards the end of our last class, and I'll give you a little reminder of what happened there. We had a second order, linear, constant coefficient, and it's also homogeneous differential equation. What we do to solve that is we make a guess. Okay, maybe it's not a complete guess, it's more of a logical argument for a solution that would work in this differential equation. It's just more fun to call it a guess. But if you take this guess for our solution to our differential equation, you take two derivatives and you plug it in, what you're going to get is this equation right here. And we did this in class a couple times. This equation here is called the characteristic polynomial. Some people might also call it the auxiliary equation. And in this case, we can actually factor this into r plus 1 and r plus 1, and we get two values for r. And each value for r gives us a solution to the differential equation. The problem here is that we don't get two linearly independent solutions. We get two solutions that are exactly the same. And we know that since this is a second order DE, we should get two linearly independent solutions to form our general solution. What we can do to fix this, just in this example, is we can actually take one of the solutions and just multiply it by t. And now we have two linearly independent solutions, and it's easy to form a general solution. Now, as I said in class, this should not work. In general, we definitely cannot take some solution to a differential equation and just multiply it by t and expect that to still solve the differential equation. In this case, it actually works, and you can check it. You can plug this y2 into the differential equation, and it checks out. But that's crazy, and it shouldn't work. So what I want to do is give you a little explanation of why this works. Okay, so let's do it. Let's explain why this works. I want to start with a general second order linear constant coefficient and also homogeneous differential equation. I also want to assume that we already have one solution to the differential equation. In this case, that one solution would have been, in our example, e to the negative t. Now the question we want to ask is, when can we just multiply that solution by t and have that still be a solution to the differential equation? So there's the question. Is t e to the rt also a solution to the differential equation? Well, we have a function and we want to know if it's a solution to a dE, so what we do is we plug it into the differential equation. That of course requires taking two derivatives, and in this case we're going to have to use a little product rule to do that. Let's do it. Again, we got these two terms because of a product rule with y, and then we got these two terms because of a product rule with just the first term in y prime. And we can start plugging things in to this differential equation. And as usual, I'm jumping through this pretty quickly, so you can hit pause whenever you like on your browser. I'm going to group all of the terms that have t e to the rt in them together and group the other terms as well. So as you can see, I grouped terms and I factored out a t e to the rt from those blue terms, and from these green terms I factored an e to the rt out. Now we're at a point where we need to understand our assumption. Our original assumption was that e to the rt solves the differential equation. Well, what does that actually mean? I'm just going to put a little side note right here in the middle of the page. If e to the rt solves the differential equation, then that means if we took two derivatives, plugged in our derivatives into the left side, all this stuff on the left should add up to 0. I'll just do it real fast. Take two derivatives, plug it into the differential equation, factor out an e to the rt. Clearly e to the rt can't be 0, so ar squared plus br plus c must be 0. Well look, that appears right there in our equation. So what are we left with? If this term is 0 here, the term that we're left with is just e to the rt, 2ar plus b equals 0. Obviously again, e to the rt can't be 0, so what we're saying is 2ar plus b equals 0. I can rearrange this just a bit and get r is negative b over 2a. So what just happened? What's the significance of this? Well, let's go back up. The question was, is t e to the rt a solution to the differential equation? We took derivatives, we plugged it in, and we found that, well, I guess the left-hand side of this differential equation could equal the right side of this differential equation, but only in the case where r is negative b over 2a. Now, doesn't that equation look a little bit familiar to you? It should actually. If you go back to your days of solving quadratic equations, like this one right here, the solution of that quadratic equation is r is that thing right there. And you'll notice that there are a couple of cases. You can have two different solutions to a quadratic equation. So that would be if this number in here is positive, you get a plus solution and a minus solution. You could get complex solutions to your quadratic equation if this number in here is negative. Or you could get a repeated solution. That happens when this thing called the discriminant equals 0. We actually get what we call repeated roots. And what are those repeated roots? Well, it's r is negative b over 2a. So wait a minute. We just decided that t, e to the rt, is a solution to our differential equation, our original differential equation, only when the root is negative b over 2a. Well, that's the exact case that we have when we have repeated roots. Whenever we have repeated roots, we do get r is negative b over 2a. So it still seems kind of magical, but it's really cool because the only time we need a second linearly independent solution to our differential equation, we can actually get a second linearly independent solution to our differential equation just by multiplying by t. The only time this works is when we have repeated roots, and that's really the only time we ever want it to happen. So I like that. I think that argument is fun. Okay, I'll give you another explanation of why this works that will lead to actually a pretty useful technique in the next video. But for this video, I want to give you a quiz, so it's just going to be a little bit of extra practice. Just find the solution to the initial value problem, this one right here. Good luck, and I'll see you soon.